So, like I was showing you up on the board, two quantities, x and y, will have direct variation if there's no y-intercept, or if the y-intercept is 0, rather. In other words, if your line crosses through the origin, then y will vary directly with x. Okay, so the equation y equals 2x is an example of direct variation. When you have direct variation, you call the slope the constant of variation. So whatever number is the coefficient to x here, that's your constant variation. So in this case, it would be 2. The graph of a direct variation is a line with the slope of a that passes through the origin. So as long as your line goes through the point 0, 0, you can say it has direct variation. So let's test to see whether or not, like, these graphs have it. We're going to do some graphing in Desmos today. So we're going to break out the Chromebook, so that'll be kind of fun. But for right now, let's just plot some points and say whether or not these show direct variation. So in order to show direct variation, you've got to satisfy sort of two conditions. One being that it's got to pass through the origin, and two, it has to have a constant slope. It's got to be linear. So let's go ahead and plot these points right here and see what we get. It's kind of faded on there, so you have to look a little closely. But the first coordinate, 1, -1, would be right here. 2, 1, 3, 3, and 4, 5. So does it appear as though this line is going to pass through the origin? No, it's going to miss that point. So the origin is this coordinate 0, 0, where the two axes meet. And if it doesn't pass through that point, then it does not have direct variation. Okay, it's still linear. All right, it's got a slope, a constant rate of change. It's just the y-intercept's not 0. All right, so for number 2, we're going to do the same thing. Now, just looking at this table, I can almost tell you for sure that it's got direct variation. Like, which coordinate here kind of gives it away? 0, 0. But you want to be careful, because if it's not linear, then it won't have direct variation. So just because it passes through the origin, like if I plot these points and they do something like this, you know, that's not going to show direct variation even though it hits the origin. So just be careful. Don't jump to conclusions here. But that's a good sign. You know, that we know one of the two conditions is met. So let's go ahead and plot these points: -2, -1, 0, 0, 2, 1, 4, 2. And so, yeah, this does appear to be linear, and it does pass through the origin. So this one does show direct variation. So this has direct variation. Because it's linear, and it has a y-intercept of 0. This one does not have direct variation, right? No direct variation. All right, so we're going to look at some equations. So what do you think would be the best way to determine whether or not some of these equations show direct variation? Like if I have y equals -2x. Put it into the calculator, let's graph it and see what it looks like, right? So that's what we're going to do. But I want you all to not only know how to use the calculator to put it in, I want you to know how to do it in Desmos as well. So we're going to break out the Chromebooks today. So yeah, just to reiterate, now that we've got Desmos up, we're going to do two things. Number one is we're going to test to see if it, what is the y-intercept? Is it the origin or not? And then also, is it linear? So let's look at the first equation. Y equals -2x. Now this one should be obvious, because this one actually fits the format of our linear functions that have direct variation, right? It's y equals mx. So we can say we're pretty sure that this is going to be direct variation, but let's just practice with Desmos a little bit. Let's so basically you click on here, and then you're just going to type in the equation exactly how it looks. Okay? So y equals negative, let's see, where's my negative button here? Do I have a negative button?
Yeah, it's right there.
Oh, wow. Negative 2x. All right, so there we go. So, what do you think?
Wow.
Does it show direct variation?
Yes.
Yes, it does. So we're going to write, of course it is, okay? Yes, y varies directly with x. Now, we don't necessarily need to write this for every single one that's yes, but for now, we'll go ahead and do it. So yes, y varies directly with x. All right, so let's do another one. Now you can leave that one up there if you want. There's not really a reason to. You can add as many equations as you want on here to sort of overlap. It'll default to like make them different colors, so you can color code them. You can color code them however you want. We're not going to get into all the little toys that you have at your disposal here, but let's just type in the next one. So this one's not as obvious, right? This one says 3x minus y equals 0. So it's not set up in that proper direct variation form, y equals mx. But what do you think? What's your gut feeling? Is this one going to be direct variation or not?
Yes.
Maybe? Okay, so let's type it in, see what we get. So I'm going to do a new expression. And go ahead and type this in. And you just type it in exactly how it looks. All right? 3x minus y equals 0. And let's hide the little thing here. And there we go. So, does it pass through the origin?
Yes.
And is it linear? Yeah, so this one has direct variation also. Now we can show this algebraically. If we want to show that we can write this in that direct variation form, that y equals mx form, we can. Here's how you would do it. You subtract 3x from both sides. That would give me negative y equals negative 3x. And then divide both sides by negative 1 would give you y equals 3x. So yes. Okay, it does show direct variation. You could show it algebraically, or you could just check the graph. I don't know. What do y'all prefer? The algebraic basically proof that it shows direct variation, or just looking at on the graph? Graph probably. All right, so let's do another one. So the next one is, this kind of got cut off, but I'm just going to assume that's a 1, unless, does anyone not have a hole right through this number? Everybody does? Yeah, I think so. Okay, so we'll just say it's a 1. Hopefully that's what it's supposed to be. Okay, so 4y plus 6x equals 1. So let's go ahead and type that in. I'm just going to make a new one. So 4y.
Wait, in the calculator, how do you make an equal sign?
So that's a good question. Okay. So the question was, if I'm gonna try to do this in the calculator. James, you with me? If I try to do this in the calculator, I only have one option. When I go to y equals, right? That's how I input equations. The limitation here is your function has to be in the form of y equals to do this, right? So like, in other words, like with number 4, I couldn't just type this in. I would have to solve it first and then type it in. You see what I'm saying? So if you're going to solve it anyway, you almost don't even need the calculator at that point because you've already shown that it's in the right form. So that's kind of why, one of the big advantages to Desmos is that you don't have to do that. You can just type it in exactly how it looks, and then it shows you what it looks like. So it sort of does all the algebra for you behind the scenes. So if you want to put it in the calculator, which you can, you have to solve for y first. There's no way to put in just an arbitrary equation in there, unfortunately. Yeah, so you're kind of out of luck. But this is still pretty easy, right? So I'm just going to keep typing this in. 6x equals 1. All right. So this is getting a little muddy here, so I'm gonna get rid of these other ones. So does this show direct variation? No, why not? It does not pass through the origin. If you want to show that algebraically, you would subtract 6x from both sides, which would give you 4y equals 1 minus 6x. And then right away, I can already tell that this isn't going to work out. When I divide by 4, I get basically negative 6/4 x plus 1/4. This one has a y-intercept that is not 0. Right? It's got this constant term, which is sort of preventing us from having direct variation. So this is a no. No direct variation on this one. But we could tell that from the graph, like, really easily. You know? All right, so let's do the next one. We've got a couple more to knock out here. All right, so negative y. Oh, all of a sudden, everything changed here. Negative y equals 15 minus 2x. What are you thinking here? Direct variation or no? Oh, wait, what happened here? I really messed something up. Equals 15 minus 2x. So yeah, take a minute, type that in. All right, so what do you think? Direct variation or no? Why not? What is it missing? It is linear here, right? But what does it not have? Yeah, it doesn't have the right y-intercept, right? It doesn't pass through the origin, so this is a no. All right, so take the next couple of minutes, and I want you to see if you can figure out 7 and 8. You know, decide on your own if they're direct variation or not. So yeah, what'd y'all get for number 7? Yes, right? If I just simply divide both sides by 3 here, I get y equals 2/3 x, right? That's the right form. Y-intercept 0. You know, going back to this one, I don't think I showed the algebra here. But all you would have to do is just divide everything by -1, and you get 2x minus 15. We got this y-intercept, so no. 6 was a no. No, I just want you to I want you to see like why it is algebraically, okay, or why it's not. So this one's a yes. What about number 8? Yes. That one's a yes. All right, so let's take a look at number 9. This one already shows you the graph, right? Does that show direct variation? Yeah, sure does. Right, it's got this y-intercept, it's linear, we're good to go. Number 10? No. Okay. So just keep in mind like what question we're actually answering here. We're not asking if it's linear, although that's a piece of it. It does need to be linear to have direct variation. But the question we're asking is, does it have direct variation, which is equivalent to saying, is it linear and does the y-intercept equal 0? Okay, so those are really the two things we're trying to answer. All right, we've got some word problems here. You guys ready to do some word problems? Yes. We can still use the graphing once we get our equation down, but the challenge here is going to be to make sure we can write the equation. It says an object that weighs 100 pounds on Earth would weigh just 6 pounds on Pluto. Assume that the weight P varies directly with the weight E on Earth. What would a boulder that weighs 45 pounds on Pluto weigh on Earth? So anytime you have a direct variation problem like this, and it says that it varies directly, you're just going to set up a proportion and solve. Okay? So in other words, if I weigh 100 pounds on Earth, yeah, maybe when I was like 12, right? So here's my Earth, and I want to compare that to how much I weigh on Pluto, which would be 6 pounds. It's kind of weird. Yeah. Not as much gravity there, obviously. We want to know if there was a boulder that weighed 45 pounds on Pluto, how much would it weigh on Earth? So you're going to basically set up a proportion like this. Now, you don't have to necessarily put Earth in the numerator and Pluto in the denominator, but as long as you're consistent across your ratios, you'll be fine. Do y'all know how to solve a proportion like this? So what do?
Use 6 times x.
Yep, we're going to use what's called the cross products property, otherwise known as the butterfly method. Yeah. We're going to multiply across and set those two products equal to each other. Sometimes it's just called cross multiplying. So 6 times x equals 100 times 45, which is 4,500. And then we just divide both sides by 6. And I'm going to use a calculator for this one. 4,500, oh. So 750 pounds on Earth.
What if you just divided 100 by 6 and you get what it would be, and then you multiply that by whatever the number is?
Yeah, that will work too. I mean, that's pretty much what we did, except we just did it in the reverse order. We did the multiplication before the division. But multiplication is commutative, so the order doesn't matter. Good question. All right, number 19. At a company, the number of vacation hours varies directly. So when you see that vary directly, that's time. Okay, we're going to set up a proportion problem here. With the number of weeks an employee works. An employee who works 2 weeks earns 3 vacation hours. Right away, I'm going to set up the first ratio. So I'm going to go with just the order that it says. So you're going to work 2 weeks. So like weeks of work or something. And vacation hours. Vacation hours? Not even days? Wow. Well, yeah, you can go on vacation for 2 hours, but be right back. I think the idea being you build it up over time, right? So the weeks of work, so 2 weeks of work earns 3 vacation hours. Find the number of vacation hours an employee earns for working 8 weeks. So the setup is a little different here with x being on the bottom, but the way you solve it will be the same. We're still going to use the cross product property and multiply 2 times x equals 24. This one you could probably do in your head. So divide both sides by 2. X equals 12. Yep. Number 20. Landscapers plan to spread a layer of stone on a path. The number of bags varies directly with the depth of the layer. They need 20 bags to spread a layer of stone that's 2 inches deep. How deep will the layer of stone be when they use 15 bags of stone? So let's set up the first ratio. So number of bags to depth. So let's see, they need 20 bags to spread a layer of stone that's 2 inches deep. How deep, so that's my unknown. We're trying to figure out how deep is it. How deep will the layer of stone be when they use 15 bags of stone? All right, so pretty easy setup here. We're going to cross multiply just like the last 2 problems. And we get 20x equals 30. Divide both sides by 20. And so I get x equals 1.5 inches.